Hi, welcome back to our next chapter, chapter number 6 on energy, energy transfer, and general energy analysis, part 2. So, previously we have covered part 1 in our synchronous lecture. So, today we will move to part number 2. Okay, so here we will study about energy balance. Okay, so energy, we know that energy can cross the boundaries of a closed system in the form of heat and work. So we have practically two systems. So the first system we call as open system, where the mass can go inside and comes out of the system. And we have another system called closed system, where only the heat and work can enter and leave. Okay, so we need to understand the difference between these two systems. So the conservation of energy principle, or we call as a first law of thermodynamics, is expressed as shown here. So total energy entering a system minus total energy leaving the system. So we need to take the positive one first, minus with the negative one, and we will get the net change in total energy of the system. Or we can write it like this. So this is a simpler form. E, capital E, IN. IN meaning is entering, and going out, we put E out, equals to, so the changes in the energy of the system. So this relation is often referred as the energy balance. So if you see the term energy balance, you need to understand that. So it's actually the calculation about the net change of total energy in the system. Okay, so energy change of the system, or we put it as a lambda E system. So the determination of the energy of the system during a process involves the evaluation of the energy of the system at the beginning and the end of the process. So we have two states. So we have initial state and also final state. So we want to check the energy difference from initial state until the final stage. Okay, so the final stage we always, sorry, final state is always denoted with E2. Okay, and initial state we always call it as E1. So the changes in the energy of the system is actually E2 minus E1. So we need to know that. Okay, so note that energy is a property. So previously we know what is property. The value of property does not change unless the state of the system change. So in order for energy to change, so the system must move from one state to another state. So that's why we call it as initial state and final state. So in between we can have various states. So the one we need to understand. Okay, so normally the energy stored, or the total energy, okay, of a system is expressed as sum of the three separate energies. Okay, so practically in the changes of energy, so we have three components. So the first one is the internal energy, okay, or internal energy. The second one is kinetic energy, and the third one is potential energy. So you need to plus all these three components in order to calculate the total energy. Okay, so you can see here. So for different uh, for kinetic energy, it has its own formula. Potential energy is own formula, and also the internal energy this its own formula. So you need to, depends on the information that given in the question. So you can calculate the total energy of this. Okay, so we can read here. Recall that U is the sum of the energy contained within a molecule of the system. Internal energy, we know there are four types of internal energy. We call it as sensible internal energy, latent internal energy, chemical internal energy, and also nuclear internal energy. Okay, so all that sums up as U. Okay, and we have kinetic energy Ke, and also potential energy Pe. Okay, so we need to understand that. Okay, so the internal energy U is dependent on the state of the system and the mass of the system. Okay, so we need to consider. So previously we have seen in the formula of internal energy, there's a word M. So M, you need to times with the mass of the energy, okay, or the molecules inside. Okay, so the conservation of energy principle or the first law of thermodynamics for closed system is written. Okay, so based on what we have seen in the previous slides, so we can come up with this equation. E in minus E out equals to changes in internal energy plus changes in kinetic energy plus changes in potential energy. If the system does not move with the velocity and has no change in the elevation, so meaning so no speed involved, is related to kinetic energy and also elevation. So elevation related to potential energy. So if the system is not moving forward or at the different height, so meaning the kinetic energy, changes in the kinetic energy and changes in the potential energy become zero. So if Ke and Pe becomes zero, finally in this equation you only have this form. So E in minus E out equals to changes in the internal energy. So we call it as a stationary system. Okay, so we need to understand that. Okay, so the mechanism of energy transfer E in and E out. We want to see something related to the energy in and also energy out. So the mechanism of energy transfer at the system boundaries are heat, work, and mass flow. Okay, so practically you have three types of energy transfer. So we call it as a mechanism. So mechanism meaning it's the way of energy transfer. First as a heat, so it can come in or it can go out of the system. Then we have work, where work similarly can come and go out, and mass flow. Mass can come in and mass can go out. Okay, so these three things will be there. Okay, in whatever system. Just we need to know that whether we want to consider it zero or not. Okay, so in closed system, for example, or we call it as a fixed mass, no mass flow because it's fixed mass, so mass equals to zero. Even though it's there, but the mass value equals to zero. So that's why in the closed system, we only have two mechanism of energy transfer, which is heat and also work. And in the open system, so you have all three. Okay, all three mass in the open system you have a mass flow. Okay, so meaning the mass flow is having a value, and you can have it and also work transfer. So you can have both. Okay, or all three you can have in the open system. Okay, so you can read here. So I'm not going to read. So I'm just going to say the important stuff. Okay, from this slide. Okay, so for heat transfer we always call it as Q. Okay, so Q is actually caused by the temperature difference. So meaning if work is done and is depending on the temperature difference, is automatically we call it as a heat transfer. Okay, so if heat energy is added to the system, we put E plus. Okay, so if it leave the system or heat transfer from the system, so these are some of the keywords. So we put it as E minus. Q equals to 0. Okay, there are some system we call it as a adiabatic system. The adiabatic system meaning in the system we have a proper insulation and no heat transfer happen. Okay, so we can have that kind of system. And for the number 2 for work, or we call it as W, capital W. So similarly, so when the weight is raised, okay, or something is moved, meaning work is done, and compared to heat transfer, here we only moving the weights, so no temperature difference involved. And then we consider it as a work. Okay, so here also when a weight is added to the system, you put it as E plus, and if the weight leave the system, you put it as E minus. Okay, so W is 0 for system having no work interaction in the boundaries. meaning our system will have a boundary. So no it comes and uh, no work is done from outside or from the inside. So meaning you can consider W as 0. But normally you will have work done in the system. Okay, the third one, mass flow. So mass flow, we call it with small m. So for mass. Okay, so if the mass comes into the system, similarly, you put E plus, and if it leaves the system, you put E minus. Okay, so you need to know that since no mass transfer occur in the closed system, we have seen earlier, in the closed system, we don't have mass transfer. So the energy transfer for mass will be 0 for closed system. For open system, we have a value. Okay, so you can see here. So we try to expand the previous equation. Okay, previous equation. So you already know Q in and Q out, W in and W out, and E mass in and E mass out. So you have three things. So you are taking all each element is divided into two, like Q in, Q out, W in, W out, E mass in, and E mass out. So you can come up with this energy balance equation. Okay, so you can see this. Okay, so all this I have explained earlier. Okay, so similar like what we studied in part one. So if you have a dot on top of this form, okay, or we call it as a abbreviation. Okay, so if you have a dot on top, it considers about the rate or the power. Okay, so the rate of the system. Normally, it will be involved with the timing. Okay, so with timing. Okay, then we have time interval. So you can also uh, times with the time, okay, in order to get the total energy. Okay, and if we, the equation is written in a smaller e, so meaning it is based on per unit mass. So E will be changed to capital E will be changed to smaller e. Okay, so it denotes that. So it will be per unit mass. So we know that clearly. Okay, another form will be the differential form, so which you can also use. So we'll see a few examples of this. Okay, so we can read here. So this will be the kind of examples that will be given. So normally we will give one system, and from the system we will give uh, some parameters, and normally one of the parameters will be not there, and you need to calculate it. Okay, so we can read the question. The rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. We have a system is a there's a closed system, and you have a paddle wheel. So meaning our work is entering. Okay, so initially the internal energy of the fluid is 800 kilojoule. So meaning initial condition is 800 kilojoule. So during the cooling process, the fluid loses 500 kilojoules of heat. So meaning 500 is leaving the system, and paddle work does 100 kilojoule. So meaning when you paddle, you are doing 100 kilojoule worth of work, okay, on the fluid. So they are asking us to determine the final internal energy of the fluid. So neglect the energy stored in the paddle. So we have a assumption. Okay, so you need to find the final internal energy. Okay, so this is the sketch. So normally, when the question is given, so I encourage you to draw this first system sketch so that you will know and you won't miss out important points. So U1 equals to 800 kilojoule. So U2, they ask you to find the final internal energy. So the information given, Q out equals to 500 kilojoule, and work uh, this is a shaft, work shaft in equals to 100 kV. Okay, so this is the formula. E in minus E out equals to changes of energy in the system. So we write back all the formula. Okay, so we don't consider, we only consider Q in and W in. So since no is a closed system, so no work done. Sorry, no mass entering the system or leaving the system. So you will have this equation. So based on this, you just substitute the value. Substitute the value is 100. So you rearrange the equation, you will get the equation in this form. Okay, so W shaft work shaft in minus Q out equals to U2 minus U1. So you just replace the value 100 kilojoule minus 500 kilojoule equals to U2 minus 800 kilojoule. Okay, so finally you can find uh, the final internal energy or U2 equals to 400 kilojoule. This is an example of question that can be given. You will see another question. Okay, so you have here positive and negative work. In part A of figure, the system gains 1500 joule of heat and 2200 of work is done by the system. So you need to highlight this kind of keyword. By the system meaning the system is doing work. So meaning energy is lost. So you need to understand that. Okay, so you have a first thing, the system, it is entering and also work is done. Okay, so they ask you to determine the change of internal energy. Okay, so based on this, so we have the formula. You only have two components, the Q in, so E decentering, and W out, work is done. Okay, so you just replace. So if it's entering, you put plus. Okay, and if out, you put minus. So both you plus. So based on this, finally, so the changes in the internal energy for the first system is negative 700 joule. So meaning the system is losing energy. Losing energy. Okay, then we move to the second part. So in part B, the system also gained 1500 joule of heat, but 2200 joules of work is done on the system. So meaning from outside work is done. So meaning energy is entering. Okay, so here you have the same formula. Okay, so here the direction will be different. The heat is entering and work also entering. Okay, so Q in plus W in. Here since in and in, so you plus both. So plus 1500 plus 2200. Okay, so the answer is plus 3700 joule. Meaning 3700 joule of energy is entering the system. So yeah, that's how the calculation is done. So the third one, a total of 135 joule of work is done on a gaseous refrigerant as it undergoes compression. If the internal energy of the gas increased by 114 joule during the process, what is the total amount of energy transferred as heat? Has energy been added to or removed from the refrigerant as heat? Okay, so meaning for here you have like a piston where you have a initial energy, okay, or the changes of energy increased by 114, meaning the changes of energy is 114 joule. Okay, so here a work is done and also the energy is lost, either loss or gain. So you need to determine this. The question can ask you that way also. So to determine based on the signs. Okay. So you have work and also heat transfer. So you just put, because since you don't know in or out, you just put Q. Q plus work in, okay, equals to changes in the energy. The Q plus, okay, work in is under 35. So since centering the systems is non-negative, okay, plus under 35 equals to 114. So if you settle this, you'll get the final answer. The value is negative 21 joule. Okay, so the sign of the value of Q is negative. This indicates the energy is transferred out as heat from the refrigerant. So meaning this is Q out. Okay, so the direction is going out. Okay, so energy has been removed from the refrigerant as heat. That's how you can conclude. So if negative, meaning is going up. It's easier to understand. Okay, so another question. Okay, air flows into an open system and carries energy at the rate of 300 kilowatt. So as the air flows through the system, we receive 600 kilowatt of work and losses 100 kilowatt of energy by heat transfer to the surrounding. If the system experiences no energy change as the air flows through it, how much energy does the air carries as it leaves the system in kilowatt? So you need to calculate. Okay, so you can do the system sketch first. So mass is entering and work is done. So W in. Okay, so you can see here got you have dot because it's related to rate. Okay, so how it is transferred. Also, energy is the mass is going up. Okay, so this is considered an open system because it has a mass. Okay, so conservation of energy. So use the same formula E in dot minus E out dot equals to changes of E dot of the system, okay, or the rate of the system. If from here you can transfer to this formula. So E mass in plus work in. So whatever arrow going in is plus. Okay, going out is minus. So here minus, here also minus, equals to changes in the rate of the system. So it says here, so no energy change, so meaning changes equals to 0. Okay, so you already know some values. So you try to first rearrange the formula. If after you rearrange, you get like this because you want to find the rate of energy of mass going up. Okay, so you just replace, so 300 plus 600 minus 100 kilowatt. Okay, so rate is in kilowatt, so you get the answer in 800 kilowatt because the answer is in kilowatt. Okay, so this is how. So the main important thing is how you formulate the equation. Okay, if your equation is right, you will get the answer right. So please be careful on that. Okay, so we are entering to the last part of the slides. Okay, so the first law for a cycle. So if you still remember what is cycle, cycle meaning you can have a various state, but the initial state and the final state must be the same. Okay, so that's what we call a cycle. Okay, so it start here, so it goes wherever you want, but it come back to the same point. So that is one complete cycle. Okay, so that one we need to understand. So in thermodynamics, cycle is composed of processes that cause the working fluid to undergo series of state changes. So from initial state to the final state, in between you can have various states. Okay? So we call, so the initial state and also the final state must be identical, means same. Okay? If both are same, so meaning no energy loss. the changes of energy is zero. So we need to understand that. So no energy loss or gain by the system. So since thermodynamic cycle can be viewed as having heat and work but not mass, so thermodynamic we are mostly dealing with heat and also work, since mass is not a part of thermodynamics. Okay, so we are more focusing on heat and also work, especially in the so this is in the uh, closed system. Okay, closed system. Okay, the first law for closed system operating in the thermodynamic cycle becomes okay. So this is the equation Q net, okay, meaning Q in minus Q out. So we also can put either letter Q or you can put net, so meaning total. Okay, so Q net minus W net equals to changes in the cycle. Since the changes in the cycle equals to zero, okay, so you can get like this. Q net equals to W net, meaning total of E transfer equals to total of work done. Okay. So, but the condition is it must be a cycle and initial and the final state must be the same. Meaning complete one cycle. You can see an example of question for this. Okay, a steam power plant operates on a thermodynamic cycle, meaning it's a complete initial and also final state in which water circulates through the boiler. So you have few states. Okay, so this real-time example. So it starts from a starting point, it goes to a boiler, it goes to turbine, it goes to a condenser, pump, then back to boiler. So you come back to the same place. Okay, so for each kilogram, okay, so the trick here it says each kilogram. So meaning you need to find the smaller number, the smaller alphabet, okay, kilojoule per kilogram. If you still remember, okay. Going through the cycle receives 2000 kilojoule. In boiler, you get 2000 kilojoule of heat and release 1500 heat in condenser in the second state and receive 5 kilojoule of work in cycle pump, the third one. Okay, so before come back to the same place. Okay, so based on this, is mentioned thermodynamic cycle. So you automatically take this equation. Q net equals to W net. Okay, so you open up the equation. So Q net equals to Q in minus Q out. W net equals to W out minus W in. Okay, so based on this, you rearrange. Okay, so they asked to find the work done by the steam, meaning by the system. So you need to find work W out. So you all these components you bring to this side, W out you bring to this side. Okay, so you get Q in minus Q out plus W in. So since it says each kilogram, so you just take per mass value. Okay, so W capital W becomes smaller W and capital Q becomes smaller Q. Okay, so you rewrite again Q W out equals to Q in minus Q out plus W in. Okay, from here you can substitute the value. So 2000 so minus 1005 plus 5. Okay, the unit is kilojoule per kilogram. Okay, so you settle this, you get so the work done by the steam in kilojoule per kilogram equals to 500. Right? Okay, so these are a few examples that you can find in this chapter. Okay, so with this, so we are coming to a conclusion of chapter 6. So it's not chapter 7, chapter 6. Okay, so try to answer the questions given, and we will see. We will discuss about this during the discussion.